Space Telescope began sending back incredible, unprecedented images of the universe. With its back to our sun, shielding itself from the saturating light of our star, it turned its massive golden mirrors to the universe, focusing the light it gathered onto cryogenically cooled sensors, peering back to the cold, distant, redshifted light emitted 13.5 billion years ago in the early stages of our universe. An incredible human achievement, but what if we created a massive radio space telescope? We could peer even further back in time, detecting signals emitted from hydrogen atoms in our primordial universe, light that even the James Webb Space Telescope can't detect. However, radio telescopes are massive. Building a collecting area this large is a challenge, even on Earth. One of our largest radio telescopes, the Arecibo telescope, collapsed in 2020 after 57 years of service as a result of two supporting cables snapping. This telescope used a natural sinkhole to shape and support the spherical dish. Radar waves from this distant past are blocked by our atmosphere. But what if we could build something like this in space, using naturally formed craters in the same way the Arecibo used its sinkhole? That is precisely the plan proposed by NASA scientists. A radio telescope on the far side of the moon, using one of the many craters pockmarking its surface. It would be the largest space telescope ever constructed, and using clever engineering, it could be vastly cheaper than the James Webb telescope. This is its story. The basic concept of a massive radio telescope is not new. The Arecibo Observatory in Puerto Rico was a huge 300-meter diameter dish. But this moon telescope would be even bigger. With a 1.3 kilometer wide crater, the engineers of this project will be able to suspend a dish with a diameter 50 meters greater than the Arecibo Observatory. This proposal is part of a program at NASA where researchers are encouraged to think about futuristic technologies that could be plausible within the next 10 to 20 years. So, how plausible is this? Building structures on the moon is not easy. The core idea behind this telescope is to use a crater on the moon as a bowl, removing the need for heavy support structures, and constructing the dish from wire meshes that naturally sag under the moon's gravity to form a reflective dish. The use of the mesh wire drastically reduces the weight of the system while still allowing radio waves to bounce off it. As long as the gaps in the mesh are shorter than the incoming signal's wavelength, the wave will bounce off. Just like the holes in the screen mesh of your microwave allow visible light to pass through, but reflect the longer wavelengths of the microwaves themselves. In order for this to work, we need to find the perfect crater, and scientists have been scouring over data obtained from the Lunar Reconnaissance Orbiter since 2009. First, it needs to be on the far side of the moon. The moon is tidally locked to the Earth, and thus the far side is always facing away from Earth, and so it shields it from the radio noise we emit. The further away the crater is from the near side of the moon, the better. To fit the 350-meter wide dish, the crater needs to be 5 kilometers in circumference and 175 meters deep. It also needs to be as smooth as possible, lacking any large boulders or mounds. The rim must also be as level as possible to allow for easy anchoring of the hanging wires. Finally, we want to point away from the center of the Milky Way galaxy, our galaxy. To observe the radio waves emitted from the early universe, we want to point our telescope to the quieter parts of the universe. But we can't point a crater. We have to rely on the moon's natural motion to sweep a section of the sky. This trace sweep changes depending on the north-south location of the crater. By choosing a crater further north, between 10 and 20 degrees, the telescope can avoid the noise of the Milky Way galaxy. These criteria narrow down the options from 82,000 craters on the far side of the moon to just 300. From those 300, 50 were chosen for more careful consideration. This crater here, almost 10 degrees north, was the chosen one. Construction on the moon is perhaps the largest challenge facing this project. The telescope is going to focus on capturing information from the electromagnetic spectrum between 4.7 MHz and 47 MHz. This corresponds to a wavelength between 6.4 and 64 meters. This leads us to one of the first engineering design constraints. The dish needs to reflect and focus these waves. On Earth, mass is not a huge constraint for a stationary structure. However, we will need to ship these materials from Earth at a huge expense per kilogram. So, we want to minimize weight where possible. We can form a support structure with lightweight carbon fiber cables. This material also helps with maintaining the structure's shape as the temperatures on the moon swings wildly from from minus 170 degrees Celsius to 120 degrees Celsius over its night and daytime cycles. A temperature swing that would cause aluminium to expand and contract, warping the shape. These carbon fiber wires will then be anchored on the crater sides, with the natural sag in the wire forming the support structure. However, hanging wires will naturally create a catenary shape, which is not suitable as a concave mirror. We need to create a shape capable of focusing the reflected electromagnetic waves to a point inside the crater, where we can hang a receiver. To get a better focused beam, the shape must be closer to a half circle. But how can we achieve that with a wire with just 2 anchor points? This is where things get interesting. Wires have no compressive strength and must hang in pure tension. Hang a wire from a single point and it will hang straight down. Hang it from 2 points and it will sag downwards until once again the entire string is in tension. But if we put more weight, it will sag with a deeper parabolic arch to allow it to remain in tension. We can take advantage of this by hanging weight strategically along its length to alter its shape. This can be done by tailoring the wire shape along its length or by coating the wire in materials of different densities along its length. But anchoring the tethers to the rim is easier said than done, especially if we're going to be constructing it without the help of astronauts. Thankfully, the moon's weaker gravity makes things easier. The moon's gravity is about 16% of Earth's. Supporting a 200 kilogram telescope on the moon is equivalent to holding just about 320 kilograms on Earth. The question is, how do we deploy them? One plan involves using dual-axle robots currently being developed by JPL to manually tow the wires into place. Another plan is to form the anchoring wire shape above the crater before landing, either by the lander firing anchors before landing or through multiple landers landing at their anchor sites. However, the cheapest option involves a single lunar lander that will land in the center of the crater and fire the anchors above the crater rim. These anchors are similar to boat anchors, and upon tensioning will dig into the lunar regolith. However, the lunar regolith is razor sharp, and great caution needs to be taken to minimize friction between the tethers and the ground. Depending on projectiles also requires extensive testing and validation to ensure their reliability and prevent any potential failures. A difficult thing to simulate, which is highly dependent on the terrain of the site. On the other hand, relying only on projectiles greatly decreases cost and complexity, with an estimated total cost of $2.4 billion. It's estimated that deploying the wires with rovers would cost $4.5 billion. For comparison, the James Webb Telescope costs $10 billion. Once deployed, these anchors are the skeleton upon which the rest of the structure is built. The antenna receiver is raised to the focal point of the structure first. If deployed by individual robotic anchor points, the tensioning of these wires could be done from the anchor points, but this again would pull the wires along extremely abrasive lunar regolith. Ideally, a robot pulley system can climb the existing anchoring wires and deploy these structures without causing any more friction on the crater rim. Next is the reflector mesh. This mesh will be made from an ultralight reflective material like gold-plated molybdenum. To deploy the reflector, guide wires are pulled to the top of the anchoring wires, which in turn will unfurl the wire mesh, carefully folded aboard, inspired by origami. This concept has been modeled in multiple space missions, from solar arrays to inflatable heat shields. With good reason. Origami, with its intricate folds, allows engineers to pack large structures into extremely tight spaces. The perfect solution for packing a 350-meter wide radar dish into a space-confined lunar lander. Once deployed, the radio telescope can begin sending data back to Earth. But this telescope won't be giving us pretty images like the James Webb Telescope. It will instead give us data on how hydrogen is distributed in the universe. But how is that useful? It will give us a new understanding of how the universe formed. Right now, the main hypothesis is that hydrogen distribution should be uniform over space and time. But that assumption of uniformity was also made about cosmic background radiation, which turned out to be false. Assumptions like this need to be tested, and not just given as a fact, and this telescope will be able to detect these hydrogens. But how? In the early universe, before stars began to form, there was no light, but there were hydrogen atoms, a lot of hydrogen atoms. Cold interstellar hydrogens are at their lowest possible energy level and radiate nothing. However, on occasion, these atoms can become excited to a higher energy state through collisions with other atomic particles. At some point, through natural decay or through a secondary collision, this energy needs to be radiated out again, and the energy is released with a photon in a very specific wavelength, 21 centimeters long, giving the phenomenon its name, the 21 centimeter line. By listening for radio waves at this particular frequency, we can quantify hydrogen formation across the universe. But the goal is more than just collecting signals from one point in time. The goal would be to track these formations over time. We can do this because of redshifting. As the universe expands, it stretches the frequencies to lower and lower frequencies. We can identify the age of the signal by how much the signal has shifted into longer wavelengths. This data is crucial for refining our models regarding the conditions that led to the formation of stars and providing insights into how the universe gradually cooled following the Big Bang. Of course, the telescope needs to send data back to Earth. This is where the telescope could potentially benefit from other lunar missions. When the Apollo astronauts ventured to the far side of the Moon, they could not communicate with Earth. The situation has improved marginally since. China launched the first and only communication relay satellite for the far side of the Moon in 2018, which is parked in the Earth-Moon L2 Lagrange point, which is communicating with their lunar lander, which became the first lunar lander to soft land on the far side of the Moon in 2019. NASA and the ESA will need their own communication relays for this mission to operate. Both NASA and the ESA have allocated substantial resources for lunar exploration. In particular, NASA's Artemis program, aiming to send humans to the Moon's south pole, is set to be in full swing in the coming decade. With the increasing number of lunar missions, communication between the Moon and Earth will become more accessible and efficient. The hydrogen mapping mission itself is only scheduled for 1 year of operation. The team is confident that they can gather enough data in that time to piece together the evolution of the early universe. But of course, the massive radio telescope is capable of much more than just detecting early hydrogen signals. The long radio wave spectrum is full of other useful information. When radio waves travel through magnetic fields, they are split and altered, and radio telescopes can pick up on this and detect and quantify the magnetic fields of exoplanets, potentially identifying exoplanets life could survive on. The team has already mapped the known exoplanet systems that traverse the field of view of the telescope. This is an exciting project with a lot of scientific potential. How could we not get excited by the potential of a massive telescope being constructed on the far side of the Moon? All projects like this begin at the same point. Before anything is manufactured, the entire design will be prototyped in a computer-aided design system, or as we call it in engineering, CAD. Before I started this YouTube channel, I spent days every week designing parts in CAD software, and I still use it for 3D printing projects. The software I use for that is Onshape. Onshape is available to try for free with the link in the description. Whether your company wants to evaluate a more modern CAD system, or you just need a CAD system for home projects, Onshape is a fantastic option. Onshape's system runs entirely on the cloud, allowing engineers and designers to work together at the same time on the same design across the world. This prevents issues with having multiple files for the same design, a problem I ran into frequently for parts I designed as an engineer, where sales reps kept sending out outdated versions of the design. No more frustrating file management or servers to deal with. Onshape also runs in a browser, which means you can use it on virtually any device or operating system, which is especially useful for Onshape's more computationally intensive applications, like finite element analysis and product renderings. Whether you are a professional engineer or a hobbyist designer, Onshape is a fantastic option for your CAD needs, and you can sign up for a free version with the link in the description.